Hello, IB. We're going to go ahead and just recap 6G1, geometric series, and then we'll enter 6G2, which is infinite geometric series. So just take a moment to think back to what 6G1 was all about. We knew we had a finite number of terms in our sequence or in our series. So we were considering if you knew that n was a particular number of terms, I could actually find the sum if I decide to add them all together, right? And these formulas helped us out. So this first formula, where the r minus the 1 subtracts from the r, is when your r value is greater than 1 or your r value is less than -1. Whereas the second formula was when your r value was between -1 and 1, all right? So again, r can't be 0, or sorry, r can't be 1. So just taking a look at a geometric series when it's finite, that makes sense. However, what happens when I want to add together an infinite number of terms? Is it possible to do that? And when would it be possible? So just something to consider. A common problem that you might have heard before is considering this frog trying to jump to the castle door. And the only limitation that he has is that every time he jumps half the distance on his next jump compared to his previous jump. So if this frog jumps once, and then his second jump is half the distance of his first jump, and this pattern continues as he tries to get to the castle door, will he actually ever get to the castle door? Okay, so in reality, we might look at this and say, well, he's going to eventually get so close that we could probably say that he gets to the castle door. However, in reality, if you actually look at how far he's going, technically he actually will never reach it because he'll infinitely be getting closer and closer and closer, but that distance can always be cut in half. So again, we've reached this idea of a limit, where we're getting so close that we can say that's where you're heading. However, we technically don't actually reach it. So how does this wind up? If I took a look at adding his distance together here, would I actually be adding an infinite number of distances? Or would I wind up just rounding it off to a certain distance from where the frog is to the castle door? Considering the two finite geometric series formulas that we've been using, think about this r value if it were greater than 1 or less than -1. So for example, if I have a ratio, maybe my ratio is 2, and I wind up raising that ratio of 2 to the nth power. So that means I'm taking 2 and multiplying it by itself n times, okay? If I continue to do this, I would actually wind up getting an infinitely large number, so it would make sense that I might be able to get an infinitely large sum. However, if I wind up looking at r when it's between -1 and 1, so for example, let's let r equal 1/2, what winds up happening when I take a small number, such as 1/2, between -1 and 1, and I raise it to a power, so I multiply it by itself n times, we know that as we multiply a fraction by itself, we're going to wind up with a smaller fraction. So eventually, that value of r to the nth power is going to wind up getting so small that we might wind up just being able to say it's going to go to 0. So our first case that we're going to consider is what happens when our absolute value of our ratio is greater than 1. So that is when r is greater than 1 or when r is less than -1, when it's an integer greater than 1 or less than -1. All right, well, if that's the case, or not even an integer, it can be a fraction as well. If n goes to infinity, so if I wind up letting n get really large, then that means that my u sub n, whatever that term is going to also wind up getting extremely large, which means my sum is going to wind up getting extremely large, right? So that's kind of the idea we were just talking about, where your r value is going to wind up multiplying by itself so many times. For example, if it's 2, that you're just going to wind up getting an even larger number. Let's take a look at that in a little bit more detail. In our first example, my u sub 1 value is 2, my ratio is 3. So if I wind up using my formula for when my ratio is going to be greater than 1, my u sub 1 value is 2, My ratio is 3 to the nth power minus 1, and I divide by r minus 1, so 3 minus 1. If I wind up simplifying this down a bit, my series formula is going to wind up being, if I reduce this, the 2 divided by 3 minus 1, which is 2, I'm just going to wind up with 3 to the n minus 1. Now, since we just spent some time graphing exponentials, I know that 3 to the n is an exponential function, and minus 1 makes it move down 1, so the horizontal asymptote is now at negative 1, and my function is going to wind up increasing exponentially like so. All right, so a rough sketch, but that's about what I'm looking at here. So if that were the case, if my sum continues to go up and up and up and up, I'm going to wind up going to infinity. So it does make sense that if my ratio is 3, so anything, again, that's larger than 1 or less than negative 1, I'm going to wind up with this infinite sum, because it's just going to continue to get larger. We call this a divergent series or sequence when it diverges away from any kind of limitation. So when r is greater than 1 or less than negative 1, our sequence in our series we can call divergent, as we do not have a limit that it approaches. So let's look at case number 2. When our absolute value of our ratio is less than 1. So our r value is going to be between negative 1 and positive 1. What is going to wind up happening? And we've already discussed a little bit. Remember, this is our example where if my ratio was half, if I continue to multiply 1/2 by itself n times, okay, I'm going to wind up with a super, super small fraction. So let's see what winds up happening in our series formula. Let's take, for example, u sub 1 is 2, and our ratio is 1/2. And the series formula that we'll use is the u sub 1 multiplied by 1 minus r to the nth power divided by 1 minus r. So if I wind up substituting in my values, my u sub 1 is 2, 1 minus, my ratio is 1/2, raise that to the nth power, and I divide by 1 minus 1/2. Let's go ahead and simplify this down. If I have 2 multiplied by 1 minus 1/2 raised to the nth power, and 1 minus 1/2 is 1/2. When I divide 2 by 1/2, remember that is going to multiply by the reciprocal, I'm going to wind up with 4. So therefore, I wind up with 4 multiplied by 1 minus 1/2 to the nth power. And last but not least, I can expand, so 4 minus 4 multiplied by 1/2 to the nth power. Now already, even if I don't know all the details, I'll know that 4 by 1/2 to the nth power is an exponential, and I'm subtracting it off of 4, which is now where my new horizontal asymptote is. So if I wind up drawing my horizontal asymptote at 4, and I have a negative exponential, so I'm going to wind up decreasing. Increasing toward the asymptote. This negative is a reflection. Remember our wonderful functions. So if I wind up reflecting, and I'm going to increase toward that horizontal asymptote, I'm going to wind up with a function that's going to wind up going up toward that limitation. So I do have a ceiling. I can't go any further past that 4. All right? So from our basic knowledge of exponentials, we know that in our case 1, we had a graph that would continue to go up to infinity, and the asymptote was below the graph. So as we look to the left, we wind up getting closer to the horizontal asymptote, but to the right, we go up to infinity. Whereas with this function, we wind up reflecting, so I wind up increasing toward that limitation or asymptote, all right? So we're getting super close. So this is what would basically be happening with that frog example. All right, therefore, if your r value is between -1 and 1, you have an infinite geometric series of the form u sub 1 plus u sub 1 times your ratio plus u sub 1 times your ratio squared, and so on. So I can just say I'm going to take the sum from 1 to infinity of u sub 1 times your ratio raised to the k minus 1 power. Okay? So we will wind up converging to u sub 1 divided by 1 minus r. Just to look at that in a little bit more detail, if your r sub n winds up going to, if your n winds up going to infinity, your r sub n, as we were discussing, is going to wind up going so small that it's going to wind up getting close to 0. So what we'll say is, if r sub n goes to 0, then what you really have here is 1 minus 0. So therefore, we come down to u sub 1 divided by 1 minus r, which is your limiting sum of a series. So you are actually getting close to, you're converging or getting close to a limitation. Whereas with the first example, we were diverging or going to infinity. So when you're working through examples, the first question you're going to have to ask yourself is, what is that r value? Because if the r value is greater than 1 or less than negative 1, we're not going to be finding an infinite sum. So if I have my first value of 1/2, and it looks like my ratio here is negative 1/4, that is within negative 1 to 1, so I can use my formula of u sub 1 divided by 1 minus your r. So therefore, I would have my u sub 1 is 1/2 divided by 1 minus my ratio of negative 1/4. And if I simplify that, I should wind up with my infinite series, or my infinite sum, as 2/5. All right? And again, I can only use this formula when my ratio is between negative 1 and positive 1, which it was. So this series is going to converge, or it's going to come towards a limitation, which winds up being a limiting sum of 2/5. All right? Hope you guys can practice one more or two. Take a look in your textbook, and we'll wind up doing a few more in class tomorrow.